So again, the purpose of this is to force you to think about these pictures and identify what are the critical parts of the picture. They've all got circles, but they've got more. So A, we've already talked about. Segments formed by tangents is best modeled by number 7, where I've got segments created by two sets of tangents meeting. And B, segments formed by secants. So that's 12. C, segments formed by secant and tangent. What's that number? 3. We've got one secant and one tangent, and we're talking about the segments formed as a result. D says segments formed by intersecting chords. Where are we seeing that? 13. These are two chords. They stay inside the circle and they produce segments when they cross like this. E, the central angle theorem. Remember what a central angle looks like? Which one?
4.
4 is correct. That's a central angle. And the reason we've got these letters is eventually you're going to get the formulas for these. And what's the relationship between A and B in this picture? If this central angle were 50 degrees, how much would this arc be?
100.
50. Central angle is the same measurement. But then F asks about the inscribed angle theorem. Which one's that? 11. And that's the one where A will be 1/2 of the arc. So again, by determining which picture you're looking at, you can determine which formula you'll need to use. G says the radius chord theorem. What do you think? You learned this last class as well, I think. What happens if a radius is perpendicular to a chord? What happens if you take a radius and you make it perpendicular to the chord? What does it do to that chord? Cuts it in half, it bisects it. So 5 is G, radius chord theorem. What about H? We're looking for a tangent radius. Where are a tangent and a radius meeting? Good. Here's our tangent. And if it meets with a radius, do you guys know what the measure of angle A is? 90, good. How'd you know? This is an example of one of the extreme inscribed angles. We'll talk about that more today. I is the Arc Intercept Corollary. Remember that one? That was an extension of the Inscribed Angles. If angle B is inscribed to this arc, and angle A is also inscribed to the same arc, then what's true about B and A? The Arc Intercept Corollary is number 2. J, angles from two secants. So now we're talking about angles and arc measures from two secants with a POI outside. What does POI mean? Point of intersection. So we're looking for two secants meeting, and we're talking about angles and arcs. 8, right? Here's two secants. They're slicing a little piece of the circle off, and we've got angles and arcs. So this is J, angles, secants. What about K? Angles formed by two chords. Good. L, angle formed by a tangent and a non-diameter secant. Well, list 6 looks to be two tangents. One, here's a tangent. And because this one goes through the circle once and then hits it again, that's a secant. And it's not like number 10, which is a diameter. So this is L, angle with tangent and secant. And then M, last one, process of elimination must be 6. Angle formed by two tangents with a POI outside. Five, I can do all these. If this were a test now, I think I could correctly match each name to the picture. 3, as you described them, I'm like, oh, that makes sense, but I'm not sure I could produce this myself. 1, I've got some gaps in my knowledge that I'm going to have to work on to be able to understand this. Okay, good. I think this is really important. Being able to distinguish the pictures helps you focus on what matters. For today, what we're going to be dealing with is arcs and angles in 3 different scenarios. One scenario is where they meet on the inside, so two chords. One scenario is where they meet on the circle, which could be like an inscribed angle. We'll talk about that. And one is where they have a point of intersection outside of the circle, which could be secants or tangents. To start with, let me draw you some pictures and get you thinking in a certain way. We've already talked about a central angle. And we've said that if I've got an arc here of X degrees, how big is that central angle going to be? The same, it'll be X also, right? Just like if you slice a piece of pizza, you get the same percentage of the set of the circle on the inside as you do in crust on the outside. If you can cut 6 slices, you've got 1/6 in the inside and 1/6 on the outside. But then I said, okay, what if we pinched this vertex and begin to drag it backwards? And I talked about what happens if we start with that same arc X, but we drag it all the way back to the point where it snaps onto the inside of the circle. What kind of angle is this now called? That is the measure of it. Do you remember what we call it? Good. This one's a central angle. This one's inscribed. We've done these before. So what we said is that when we pinch it and pull it back, it gets smaller and smaller until it achieves half the size. What I want to talk about today is what happens in between those, right? It's no longer at the center. We've already started pulling it back, but we haven't yet achieved the inscribed. What do you notice about this arc versus the arc we marked as X? It's smaller, right? It had to change. Can you visualize that I could have taken the radii we used here to create the central angle and I could have extended them to make them diameters. And if I had done that, because these two angles are vertical, how big is this angle? It's X. And then how big would this arc be? Because this is now a central angle facing this arc. X. Now, I'm going to ask you to think about the formula we talked about for central angles, that the angle is equal to the arc, instead a different way. I want you to think about it as these two angles together add up to these two arcs together. Do you agree that that's still true? Now let's come look at the inscribed angle. As I pulled it back, this other arc back here gets smaller or larger as I continue to pull it back towards inscribed. Smaller. When it reaches this point, what is the size of the arc over here? 0. We've pinched it away, haven't we? But theoretically, isn't there a vertical angle in there somewhere? And if this is 1/2 x, this vertical angle would also be 1/2 x. And these two together, these two central angles, not central, inscribed angle and its vertical angle pair, add up to x. And what do the two arcs add up to? 0 plus x is x as well. So that rule that I just described, where the arcs add up to the same as the vertical angles, applies for this as well. So what do you think is the measure of this arc, excuse me, this angle in here? Well, why is this one here? And if this were a central angle, then you're right, it would be y. But then it would have to be the same as this one because they're vertical, and that would mean this would have to be y. Another way to think about this is this angle the average of these two? X plus x is 2x, divided by 2 is x. X plus 0 is x, divided by 2 is 1/2 x. So what's this one? It's the average of those two. So this is our first formula over on the front side here. The interior is if I want to take angle 1, its measure is going to be the average of the arc it meets on this side and its vertical angles arc on this side. So 1 is going to be 1/2 the measure of arc AD plus the measure of arc BC. Would you please fill in the formula for B, excuse me, the measure of angle 2 there in terms of its arcs? Still going to be half of two things added together. What are the two things that are added together here?
AB and CD, or the measure of arc AB and the measure of arc CD.
Good. So what about number 1? How would you do that problem? Just a straightforward application of it, isn't it? 1/2 of these two added together, 109 plus 45. So 1/2 of 154, 77 degrees. I'd like to suggest that, I mean, you guys know me by now, I'm really visual. So I'd like to suggest that we consider this formula. The angle is 1/2 the arc plus the other arc. It's kind of a pictograph formula, but it's a little bit more generic. And it'll help us in solving problems like, for example, number 4. Take a look at number 4. What's wrong with it? How's it changed? Yeah, they changed what you're looking for. It's not an angle anymore, it's looking for an arc. But if we use this pictograph type formula, the angle is 1/2 the measure of an arc plus another arc. The angle is our unknown. No, excuse me, it's not. We know that it's 62. 1/2, we know one of the arcs, 74. The other arc is our unknown, so I'm going to put an X there. Now it's just algebra. Would you know how to solve that algebraically?
Yeah, you would do 1/2 plus 74 and 1/2 times
You could do that. You could distribute it. Personally, you end up with 1/2 x. That's never fun for me. So instead, I would picture solving to get x by itself. You've got this plus 74 you want to get rid of, but we can't get to that until we get rid of the parentheses. Those are being multiplied by 1/2. What's the opposite of multiplying by 1/2?
You can just multiply by 2.
Multiply both sides by 2. On the left side, it becomes 124. And on the right side, it becomes, instead of 1/2 of this, it's now double that, so it just goes away. It's 74 plus x. Then we can subtract the 74. We get x is 50. Five, I feel good about solving interior intersecting angles. 3, I get it. I want some practice because some of these mix-up ones are hard. 1, I don't get this. Okay, good. Please flip to page 2. And before we get into that, let me do a little more drawing. We talked previously about inscribed angles, right? If this is 100 degrees here, how much is this angle here? Nope. It would be 100 if it were a central angle. This is not a central angle. This is inscribed. How much is it? No one? Bueller? Thank you, 50. In other words, if I pull it all the way back to the edge, it becomes half the size of the arc. And isn't that true even if I move that vertex? So if I move it over to here, isn't it still 50? What about if I move it over to here? Is it still 50? How far can I push that? Is that still 50? What if I were to like zoom myself in so that here's my bottom point down here. And I found the point that was right next to it. And I drew that chord over to this and then created my angle. Would that also be theoretically 50 degrees? Is that still an inscribed angle? It is. This leg of it is just super hard to see because it's just connecting 2 points. What if I took it one step more? What if I went from that other point straight across and stopped here on the blue one? Is that still an inscribed angle? No, I've lost the other leg of the angle, haven't I? But what if I then used a tangent to create the perfect leg through that point that only touches that point? I've recreated that leg and this would still be 50 degrees. This is what I call the, yeah. So what I'm saying is if I take a circle and I've got a tangent running through here, and if I create this extreme angle such that this is, I don't know, 60 degrees, I'm contending that the arc that it cuts here is like an inscribed angles arc. It's going to be double or 120. Now, let me prove this to you further. This was a straight line, right? How much is a straight line in degrees? 180. If I've already used up 60 degrees, how much is left for this part? 120. And if my contention that this is an extreme inscribed angle works, then this 120 degrees is an inscribed angle leading to this arc. So how big should this arc be? 240. And notice that this 240 plus my previous 120 makes the 360. Just as this 120 plus the 60 makes my 180. So let's go to page 2, top of page 2. So what we're saying here is that angle 1 is equal to an extreme inscribed angle to this little arc here, which means it's going to be half the measure of that arc. Half measure of AB. And then angle 2 here is an extreme inscribed angle to what arc? ACB, really good. You recognize that this is a major arc, and therefore it requires 3 letters, not just 2. And again, I call this the extreme inscribed angle. I think it's helpful. I mean that an inscribed angle is where I drag it back onto the circle, and that I can keep moving that closer and closer until I'm right next to it. And in fact, the extreme one is when I go straight across as a chord and bring in the tangent. It's still an inscribed angle. It's half the measure of that arc. So what's our answer to DEG here?
Would be 1/2 of the measure of arc EHB.
Yep,
Which is 308. So measure of angle DEG would be 154.
exactly. What about number 9? Take a look at number 9, see how you would solve that one. There's 2 ways you can look at this. What we're looking for, what we're trying to find is this arc right there, right? This pink arc I've just sketched. Does somebody see a way to get at it? Yeah.
You use an angle on the other side, which is like 151,
Right?
and then you minus that from 180 to find the angle of DXY.
Good,
And then you would double it.
good. So the arc would be 29 times 2, which would be 58. That's exactly right. Did anybody see a different way to do that one? Yeah.
Could you find arc y dx and then subtract?
Exactly. 2 times 151 is 302. And then say that this one would be 360 minus 302, which is 58. Same answer, just found 2 different ways. Either way works. Any questions on solving problems with the intersection, the POI, on the circle, what I call the extreme inscribed angle? Okay, last one is what happens if it's not in the center, right? That's a center angle. It's not like averaging them. It's not all the way on the circle, the inscribed. It's now been pulled out, so it's outside of the circle. First of all, is this angle getting bigger or smaller, assuming that the arc is staying the same? Smaller and smaller. It's really small here now. So what we're going to find is it's still kind of like the average we had before. We're still comparing 2 arcs. This time one is decidedly bigger than the other one, but we're going to subtract them. So the measure of CE minus the measure of BD. And it turns out that this one's going to be the exact same formula. We're still going to be able to take the big arc minus the little arc and then take 1/2 of that. And it even works for this third case as well. So please do number 11 really quickly. It should go pretty fast. Easy peasy. Please go to number 19. Try number 19. I want to show you one more thing. What makes 19 harder? What'd you discover is the problem with this one? Only has one of the pieces. We're missing a piece, right? Like even if we use our pictograph and say that the angle is 1/2 of the big arc minus the small arc, we could say the angle here is the unknown. We know the big arc, but we don't know the small arc. Or do we?
Will it just be 360 minus 313?
It would, because these are tangents, right? It wouldn't work that way for secants because in secants, it's lopping part of the circle off. But when they're just tangents, the little angle, the arc, excuse me, the little arc and the big arc together make up the full circle because the tangent doesn't lose any of the circle's edge, just hits one point. Yeah. Yeah, exactly. But let me show you something else that's kind of cool. What is that? 47. So that means 313 minus 47, which is 1/2 of 260, 256, 266. Thank you. Which would be 133. Now, what do you notice about the difference between 133 and 313? Subtract them. What do you see? It's kind of an interesting number, isn't it? What's 313 minus 133? 180. That's a big number in geometry. Does that always happen? Let's see. In the event that I've got two tangents, and we know that this arc is X, how big is this arc relative to that? 360 minus X. And if we're looking for Y over here, what we're saying is that Y is 1/2 of this big one minus this littler one. Let's distribute the minus. Distributing a minus over a negative X would make it positive X. So 2X minus 360, take half of that and we get X minus 180 in all cases. So pretend that these are both tangents, really poorly drawn. And let's say that I tell you that this is 250. What's the value of X? Almost. You can do it the long way, but just subtract 180. What's 250 minus 180? 70. Or you could have done it the long way and said 360 minus 250 is 110. And half of 250 minus 110 is equal to half of 140, which is 70. Either way works. It only works on two tangents, right? Where you've got the big one given to you. Turns out it'll work on this one too, but it just subtracts the other way. You'll subtract this from 180. So if this is just marked on 106, we know this is going to be 180 minus 106 is 74. Okay, your homework is to finish up this packet, submit it as well as the warm-up in Canvas. If any of you have a test that you want to make up or finish or take again, today's a good day for that. Yes.